Welcome everyone to Carleton Connects, the college's monthly webinar that connects you with new and engaging work being done on campus by faculty and staff and out in the world by emeritus professors and alumni, young and old. I'm Christopher Brunel in the Office of Alumni Relations. And as always, Carleton Connects offers you, the audience, a chance to connect with our speakers and to ask questions during or after the talk. You can use the chat feature at any time to send in your questions and your comments. Our guests today are three professors, Kim Smith, Dan Maxbauer, and Toivo Kallas. Kim Smith has taught political science and environmental studies here at Carleton for over 2 decades. She's an award-winning author, and her most recent book is on the conservation movement and constitutional change. And she recently received the Lifetime Achievement Award from the Association for Environmental Studies and Sciences. Dan Maxbauer is a member of Carleton's Geology Department, where he teaches courses on historical climate change and paleoclimatology. His publications focus on how we can understand the climates of the past through magnetic and geochemical analysis. And Toivo Kallas is a distinguished professor emeritus of microbial genetics and biotechnology at the University of Wisconsin-Oshkosh, as well as a distinguished member of the Carleton class of 1970. He's a co-founder of Algoma Algal Biotechnology, and he's working on the design of a photobioreactor that would allow algae to capture carbon dioxide. Kim, Dan, Toivo, welcome to the show.
Thank you.
Thank you, Christopher. So I'm going to kick things off, so I'll share my screen for you all. I hope you can see what I'm seeing. My name is Dan Maxbauer, as Christopher said. I'm an assistant professor in the geology department here at Carleton. It's great to see so many alumni gathering today virtually to talk about these things. We're all going to attempt to be fairly brief in our opening remarks so that we'll have plenty of time to answer questions and have a discussion with you all. And what I'd like to talk about today represents a new line of my research and something that I'm excited to get started on this coming summer. And there's 4 things I'd like to try to address in my short time. First would be why we need carbon dioxide removal. I'll introduce what enhanced weathering is. I'll tell you a little bit about the field trials that we're planning to initiate at Carleton. And I'll say a little bit at the end about what potential enhanced weathering has as a carbon sequestration tool for Carleton and for the state of Minnesota. So to kick things off, why do we need carbon dioxide removal? I'll make the case with this graph. This is the rise in CO2 in the atmosphere over the Common Era. And the blue data points are from the Law Dome ice core in Antarctica. Those are measurements made on gas bubbles trapped in the ice sheet. The gray symbols represent direct measurements of CO2 concentrations in the air at the Mauna Loa Observatory in Hawaii. And you can see that there's a sharp increase in CO2 in the atmosphere since the Industrial Revolution, and particularly over the last 70 years, CO2's increased by 100 parts per million in the atmosphere. And I'm a geologist. I've spent a lot of my professional career thinking about past climates and past perturbations to the Earth's carbon cycle. And geologic perspectives tell us that this increase in CO2, the rate that CO2 is increasing, is unprecedented in the geologic record. CO2, of course, is an important greenhouse gas. And so it's imperative that we work to slow and reduce the rates of our carbon emissions in an effort to limit future warming. And there have been a variety of reports over the past several decades, and more recently, a recent IPCC report in 2018 that emphasized these points. Okay, so what is enhanced weathering? Enhanced weathering is a well-known geologic process of simple chemical weathering of silicate minerals, where a silicate mineral, here a calcium silicate, dissolves in reaction with carbon dioxide and water to produce calcium bicarbonate, both ions in solution, and some silica. And the calcium here is a placeholder for nutrients or other types of cations that might be released, say magnesium or potassium. And the bicarbonate represents alkalinity, so that's going to increase the pH of the system. And the important thing to keep track of with applications of enhanced weathering is the bicarbonate. So that's where the carbon and the CO2 goes, is to this bicarbonate ion. And that can either form a mineral, calcium carbonate, CaCO3, in the soil, or it can drain and be transported to the local watershed. And both of those pathways represent a stable sink for carbon dioxide on human timescales, so hundreds to thousands of years. And this, of course, is how chemical weathering occurs with silicate minerals at the surface of the Earth everywhere. And this is a slow background process that's always occurring and is a well-known geologic feedback on the Earth's climate, or negative feedback on the Earth's climate, that folks are thinking about trying to enhance by application of silicate rock powders in agricultural soils. And the enhancement comes by increasing the rate that this process is occurring at, increasing the rate of that chemical reaction that consumes carbon dioxide through application of these finely ground rock powders that increases the surface area for that chemical reaction to occur. There's some constraint on the carbon sequestration efficiency of enhanced weathering of about 0.2 to 0.4 metric tons of CO2 per ton of rock dust that would be applied to an agricultural soil. Those numbers and all of the supporting information around enhanced weathering, much of it is largely theoretical and built on models or laboratory experiments. And there are very few field data that are available from field trials with appropriate monitoring to keep track of these things. And so that's a real limitation currently of understanding the potential for this technology, is a lack of field trials. So that's why we're excited to get one initiated at Carleton. There are also co-benefits I'd like to just mention. If anyone has questions, I'd be happy to say more about this. By adding these silicate rock powders, there's pretty well documented improvements to soil qualities and soil health, and increases in crop yields through the delivery of additional nutrients to the soils. So there's potential benefits for the agricultural community in addition to these benefits for carbon sequestration. All right, so the field trials we're aiming to initiate at Carleton, we hope to get started this coming summer with the first application of rock powders occurring in the fall of 2021. The study field of interest is outlined in yellow. This land that's owned by the college, and it's operated currently by Mike Peterson of Peterson Farms that you can see is located just across the street. So Mike has been an integral partner in this work. We just submitted a grant yesterday, actually, to the state of Minnesota to support this research. We're eager to get this off the ground. Here's an example of what this experimental setup will look like. We're going to distribute different treatment plots of various application rates, 10, 4, and 2 tons of rock powder per acre. And we're going to instrument each plot with a variety of things that will allow us to study the chemistry of the soils and the chemistry of the water that's draining through the soils. The application of rock powder requires a source, and we're lucky that Carleton is located just 80 miles from an active basalt quarry in Dresser, Wisconsin. And so we're going to be utilizing a local source material. And it's worth mentioning as well that these rock powders are produced as a waste product during gravel aggregate production. And so we're utilizing a waste material from pre-existing operations. Here's just a schematic to give you a sense of the things we'll be measuring and monitoring: soil water, soil carbon, soil respiration, which represents the flux of CO2 coming out of the soil surface. We'll be looking at different parameters related to the crops, mostly crop yield. And as I mentioned, we'll be monitoring and keeping track of soil properties related to soil health. Okay, just to say a little bit to conclude here, what you might be thinking, what's the potential for carbon sequestration using enhanced weathering? This plot is showing you sequestration potential in metric tons of CO2 on the y-axis relative to the land area that would be treated at various application rates shown by the different line colors. And I'll just focus your attention on one scenario for Carleton. Carleton has a climate action plan aimed to reduce carbon emissions by 2050 to reach neutrality. And part of that requires reducing what are called scope 3 emissions, which are carbon emissions associated with activity of the college, but for activities that Carleton doesn't control the energy source for. So things like travel. And that represents 6,500 metric tons of CO2 a year. So if Carleton was trying to offset some of that scope 3 emission using enhanced weathering, a useful metric would be that at 10 tons an acre, it would take something like 333 acres to sequester 1,000 metric tons of CO2, assuming the efficiency sort of in the middle of the road between the range of 0.2 to 0.4 metric tons of CO2 per ton of rock dust. For perspective, the Arboretum on campus currently is accounted to sequester 903 metric tons of CO2 per year across the 800 acres of land in the Arboretum. Okay, so for the state of Minnesota, we could imagine scaling this up to a state level. Sequestration potential here is in millions of metric tons of CO2 per year. And the x-axis now is the percentage of Minnesota agricultural land that would be treated. There are 26 million acres of agricultural land in Minnesota, and treating 33 to 50% of the agricultural land in the state at 10 tons an acre would be enough potentially, depending on sequestration potentials, to sequester all 35 million metric tons of CO2 that are associated with agriculture in the state. There are some key uncertainties, namely the sequestration efficiency is pretty critical to understanding the potential of this technology, and determining an official offset program utilizing enhanced weathering to make the cost structure make sense for the agricultural community is another big uncertainty and a topic of future work for sure. I'll conclude there, and I'm going to stop my screen share and turn things over to Toivo.
Okay, hello, Toivo Kallis here, and I'd like to thank Chris for organizing this discussion. Also a couple of classmates, Kathy Dawes and Joanne Reike and others were trying to get this set up for our June reunion. It was delayed a bit, but here we are. All right, so I will spend the next few minutes talking about the potential and challenges of using algae to capture carbon dioxide. And let's see, our images are blocking the, there we go. Oops, okay, all right. And in particular, a novel photobioreactor design that we think could change the game for algal CO2 capture and make that widely applicable. Okay, let's see, how do I advance? Here we go. All right, so I'm not going to say much about the need to address climate change. I think we're all aware of that. Fortunately, the US is going to be back in the game in the 2015 Paris Climate Accord, and so we can look forward to positive developments from the federal level in that regard. So what about algae and cyanobacteria? Cyanobacteria are blue-green algae, as you may know. And you may not know that they're responsible for much of life on Earth as we know it. Some 35 billion years ago, cyanobacteria invented oxygen-producing photosynthesis. They figured out how to extract electrons from water, and that left behind oxygen, which made much of the rest of life on Earth possible. We're dealing with microalgae here, so on the order of a few micrometers in diameter. Some of them have up to 10 times the photosynthetic efficiency of land plants. Many are fast growing, highly robust. They can tolerate high light intensities, which are lethal to many algae and plants. Some of them can double their mass in as little as 2 hours. So that's phenomenal. Also, many of them have high value biomasses and bioproducts, such as spirulina for nutraceuticals and so forth. Okay, there are existing algal mass cultivation systems out there. And these fall mainly into the category of open ponds, such as what we're seeing on the left here, cyanotech in Hawaii. These are relatively low cost, but also low yield. They're susceptible to contamination. And then we have photobioreactors where algae circulate in tubes. They're more productive than open ponds, but also more costly. And still a main limiting factor in algal production is that these cultures are relatively dilute because it takes photons, carbon dioxide, or other nutrients such as nitrogen and phosphorus to grow algae. If one of them runs out, the algae stop growing. So it's difficult to get photons, for example, into these reactors. Something to keep in mind, it takes 1.8 tons of carbon to produce 1 ton of algal biomass. All right, so a big challenge for running these algal cultivation systems is poor mixing, either in open ponds or in existing tubular photobioreactors. That limits light penetration, nutrient uptake, and thus limits the growth of the algae. And that's because the motions that are generated, the turbulent motions in these photobioreactors, culture systems are not sufficient to mix the algae to any great extent. So our solution is what's called the growth enhancing mixing spectrum technology that removes these constraints. It generates very efficient cross tube flows. And so it alleviates these problems of light penetration, nutrient uptake, and so forth. And also it's scalable in principle to very large diameter tubes. You may have noticed from the previous photos that these photobioreactors have narrow diameter tubes. That's so light can penetrate. That's a major limiting factor. All right, so what do these look like? Here is a demonstration on the left, 500 liter GEMS photobioreactor. That's my colleague, Robert Falco, in the background in his lab at Solar Clean Fuels in Arizona. That's where I am currently. He's a former Michigan State professor, engineering professor with expertise in fluid dynamics and turbulent flow. And he's come up with this interesting design that generates these cross flows. The basic idea is that there are helical grooves in the reactor tube. So even at very slow flow rates, particles, algae move across the diameter of the tube. And I'll show you how that works in the next slide. These can also be made with low cost flexible tubing, which greatly reduces the cost of these. All right, so here, what I'm going to show you, bottom left, typical smooth tube photobioreactor. And what we're looking at are dye polymers. And if I run this video clip, you'll see that particles, dyes that are on the surface, stay on the surface, ones in the middle, stay in the middle. That means for algae, ones on the surface may get too much light, they'll get photo bleached, they'll die. The ones in the middle will not receive any light after a while, so they can't grow. In contrast, what the GEMS design does, if you follow some of these particles, you'll see that they move across the diameter, same flow rate, same diameter, and we think that's what can really change the game with these photobioreactors. We believe we can greatly increase productivity, maybe at least 5 times or more relative to open ponds at comparable capital costs of building these things. And if we can do that, that'll be important. It doesn't stop. Okay, all right, so do these things actually work to grow algae? Well, the answer is yes, they do actually. My colleague and his family spend their summers in Los Alamos, New Mexico to get away from the heat of Phoenix. And with no other options available, he was able to set up a photobioreactor trial in a horse paddock. There you can see the horse. On the right, you see a GEMS photobioreactor, a smooth tube bioreactor. And we ran these tests in August. Conditions were not favorable. Snow fell, freezing temperatures, but nonetheless, we were able to grow algae. And you can see from the color that the GEMS reactor after several days did considerably better than the smooth tube reactor. Plotting these data, so cell density is a function of incubation time over the course of about a week. Red circles, growth of a cyanobacterium in the GEMS reactor relative to smooth tube reactor. And so the GEMS outperformed the smooth tube controlled by a factor of 2 to 1 or more. What's next? We currently have funding from the US Department of Agriculture to develop and scale these reactors. So here in the Fountain Hills lab in Arizona, we're setting up several different 45, 50 liter configurations, different groove depths, flow speeds, and so forth. And then these will be scaled to 500 liters. And then the most successful of those will be moved out into the field for agricultural applications, industrial CO2 capture, wastewater remediation, and potentially even green walls in your backyard so you can help do your bit to ameliorate climate change. So applications, carbon capture from clean sources such as biodigesters, ethanol plants, breweries. These are very clean sources of carbon dioxide. Those can be used to produce algae for feeds, foods, nutritional supplements. So spirulina and chlorella, algal biomasses, for example, can sell for up to $30 a kilogram. So certainly something that can help monetize the carbon capture process. Carbon capture from industries, foundries, cement plants, a lot of carbon dioxide produced there. We ran a demonstration. Here I am suited up for work in Wapaka Foundry in Wisconsin last year. And we showed that we could grow our algae on their foundry flue gas emissions, also on wastewater. What to do with that biomass? Well, there are a number of things you can do, and we can talk about that further. But one can use hydrothermal carbonization or hydrothermal liquefaction, which essentially recreates in a short time frame the geological process of making solid and liquid fuels. And then finally, air CO2 capture. There's some cyanobacteria that can grow quite fast just on air. These reactors can be deployed in farm furrows, or again, potentially as green walls in your backyard. Just some illustrations of what these might look like. Here, vertical GEMS reactors on buildings, power, radio, cell phone towers, deployed in existing open ponds in the water surrounding industrial plants. And here's an illustration of a couple of 1,000-liter GEMS photobioreactors. Oops, a little bit too far. Oh, what happened? There we go. Okay. Relative to a person, and these are ones that might be deployed in your backyard or at your business. Okay, just to wrap this up, scope and potential of these. So again, something on the order of 40 gigatons of carbon dioxide in the Earth's atmosphere. And US and global emissions, about 50% of that come from industry and power generation, 50% from non-point sources. So to address carbon in the atmosphere and remove it, we need to address both concentrated sources and dilute sources of CO2. What would it take in terms of algal reactors to have an impact? At the iron foundry in Wisconsin or Clarksdale, Arizona cement plant, these produce greater than 200 tons of CO2 per year. If we can envision 2 grams dry weight algal biomass production per liter per day, that could translate to on the order of 800 tons of CO2 captured per acre per year. And so it would take something on the order of 300 acres or maybe up to half a square mile to capture 100% of these emissions. With vertical reactors, that might be less. What about at a typical household? So carbon footprint in the US, about 16 tons CO2 emission per year. 1,000 liter airlift GEMS photobioreactor using air CO2, natural sunlight, could easily capture 1/3 of a ton of CO2 per year. If you can funnel your CO2 from heating or cooking emissions into that, that could be twice that. And if you have solar panels and use LED lighting, then that might be a ton of CO2 per year. So 5 of these guys could capture 5 tons, so a significant impact on household carbon footprints. Just for comparison, if you have a 7 or so kilowatt solar panel on your roof, that is equivalent to eliminating about 10 tons of CO2 from the atmosphere. And I think with that, I will wrap it up. There are other things we can talk about what to do with the biomass, but I want to leave time for Kim to talk about policy and such, and then be happy to come back to questions. So let me finish my part here and stop screen sharing, and thank you.
Thanks a lot to Toivo, and thanks to Christopher and Dan, my fellow panelists. I also want to take just a minute here to acknowledge that Carleton stands on the homelands of the Wapatuke and Mdewakanton bands of the Dakota Nation. And so I want to express my gratitude for their stewardship of these lands throughout the generations. And I also want to acknowledge the ongoing injustices that my communities have committed against the Dakota Nation, and my wish to interrupt that legacy with acts of healing. And addressing climate change, I think, can be one of those acts of healing. So that's some of the context for the work that I do. So my role here is to talk about how the 2020 election affected opportunities for climate policy. And I'm not going to challenge the consensus among experts that Biden's win doesn't greatly increase the odds of getting major climate legislation from Congress in the near term, because of course, even if the Democrats take the Senate in January, they'll still have a very narrow margin to work with. I do think we're seeing more Republicans talking about climate change and trying to develop a policy approach. So far, I'm not seeing a whole lot of interest from federal level Republicans in something like a carbon tax, which I think is the policy right now with the most support. But I'm not here to paint a bleak picture about climate policy. On the contrary, I think that the climate movement's focus on getting a standalone federal law has kind of distorted and obscured the progress that the United States has made on climate policy. So this chart here shows American greenhouse gas emissions from 1990 to 2017. So this is total annual emissions, not including carbon sinks. The 2018 estimate is 6,600 million metric tons of carbon dioxide equivalent, but that dropped in 2019. And of course, we expect to see a pretty big drop of about 10% in 2020. So what's driving this downward trend is a combination of technological, economic, and public policy factors. But I want to talk about policies because policies help to shape the technological and economic trends. And my main message here is that most policy responses to climate change are going to have to come from state and local government. And why is that? Well, the way I see this is kind of how I think about climate change. We're in the midst of an energy transition. And this is a term I'm borrowing from Václav Smil. It just means a major shift in our energy system. The last time we did this, was the period from about 1900 to 1930, when we shifted almost entirely to fossil fuels and we built our national grids. And what we can learn from that period is that the federal government was the last player to join the game. A coalition of local policymakers, engineers, and business leaders did most of the actual work of getting rid of individual coal furnaces and creating the large centralized power stations that we have today that were safe to operate. This coalition also worked to build roads that could be used by automobiles and develop the infrastructure needed to support cars instead of horses. And we're going to need the same sort of work today. We need to change zoning plans to allow solar and wind farms. We need to change building codes to promote energy efficiency. We need a whole new infrastructure to support electric cars. In fact, Michael Gerard and John Dernbach, legal scholars, have identified over 1,000 federal, state, and local policies that could help address climate change. And they've compiled them in this very handy book. There's a website as well associated with their work. And that website has close to 2,000 model laws for every level of government, from federal government down to state, county, township, right down to like your local school district. There are huge areas of American law and policy need to be reworked. And so obviously a single standalone federal carbon tax won't do it. Fortunately, this work has been going on in the United States since 1990. And I don't want to spend too much time on this, but I just want to remind everyone that the American states and local governments have actually been creating climate policy since about, well, actually even before 1990. So these figures just come from a comparative study of American climate policy from 2000 to 2016. And it focuses just on policies that promote renewable energy. And the message here is that the United States actually has been producing a number of different policy instruments. So this is figure here is 147 policy instruments. The other chart has to do with how ambitious the American policies are. It's a little bit less ambitious than Canada, for example. So what exactly are state and local governments doing? Well, really, they're doing more than I can possibly begin to talk about in 10 minutes. So I'm just going to talk about a couple of these areas. So in energy, as of April 2020, 26 states have passed legislation mandating energy efficiency measures. 15 states and territories have taken legislative or executive action to move towards 100% clean electricity. The emerging standard is committing to 100% carbon-free electricity by 2050, which is, of course, Minnesota's current goal. And as a result of these kinds of actions, 1/3 of Americans live in a state or city that's committed to 100% clean electricity. Now, carbon-free transportation, of course, is a lot harder, but this graphic shows that almost every state is incentivizing electric vehicles by now. In 2019 alone, 43 states in Washington, D.C. took actions to develop electric vehicles and charging infrastructure. California, along with 12 other states, adopted a zero-emission vehicle standard. And other actions include spending on charging infrastructure, reforming electricity rates to support electric vehicles, and procuring electric vehicles for public fleets. So, what should the Biden administration do if it can't get a carbon tax through Congress? Well, for sure, the administration should tighten existing regulations on air pollution. Now, the Trump administration revoked and replaced the Obama Clean Power Rule, which did target carbon emissions. The weaker rule is currently under judicial review, but everyone agrees that the technological and economic situation have changed a lot already, so we really need an updated rule. The administration can also give California permission to set its own fuel efficiency standards, which of course is permitted under the Clean Air Act. The Trump administration pulled that permission, but the Biden administration can easily renew it. And because California is such a large market, automakers really have little choice but to meet those standards. The administration can also secure funding for new technologies, and this actually does have bipartisan support. Even when the GOP controlled Congress during the first 2 years of Trump's presidency, Congress voted to increase funding for renewable energy for the Defense Department and to increase funding for research into new energy technologies. And the third thing I would just suggest is supporting these state, local, and private efforts at climate policy. The federal government can provide technical resources, and it can use its regulatory powers over energy markets to reinforce state climate programs. So the message I want to give you is that we should really be optimistic, because one thing that we've learned over the years is that the secret to reducing carbon emissions is trying to reduce carbon emissions. Pretty much everyone who tries is finding themselves, having success in reducing emissions. So I want to just end there because I really want to get to your questions.
Kim and Dan and Toivo, thanks very much for your presentations. And just as each of you has pointed out, that the climate crisis is going to take a number of different strategies to deal with it. It's really wonderful to be able to hear about a wide range of opportunities that are coming to us. Lots of people have been sending in questions. We got a lot of questions in advance of the show. We'll see how many we can get to. Dan, one of the questions that came in for you, several people were wondering if you could say a bit more about the health aspects of your project that you're working on. Is the traveling of dust an issue? Do the silica inhibit the growth of the crops, et cetera?
Yeah, thank you. I looked through I was trying to keep up with the chat. It's great to see so many questions coming through. Just to address a few of those points, there are two different ways to apply these silicate powders. One would be to apply the rock powder and then to run a machine that tills the soil and mixes it into the soil. For those of you who are familiar with agriculture, there's been a big shift to trying to minimize tillage in agricultural systems. And so we're not going to use a tillage approach, because the field we're going to be working on is a no-till field or a minimal till field. Tilling the rock dust in would certainly reduce any risk of dust being transported into the atmosphere. One of our strategies, because we've thought a little bit about this and we're a bit concerned, is to apply this, and then Mike is going to be laying the fertilizer and other soil amendments that are applied in on top of the rock dust to put a layer of material on top. And we're applying it in the fall with hopes that the snowpack over the winter helps the material accumulate into the soil. But that's one of the potential side effects that we're concerned about and folks have thought about. We think it's not likely to be any bigger of a risk once it integrates in with the soil than any other soil amendment that gets applied. Farmers have been applying crushed limestone and gypsum for decades with the same type of strategies. And then in terms of the crop yield, just to say that that's one of the best documented impacts of applying rock dust, is that it boosts crop yield. So it's a benefit. The silica can be drawn up by the plants, and it can help actually with resistance to pests and things like that. So there's other co-benefits and things that are perhaps better documented than the carbon capture rates in agricultural settings.
Thanks. Toivo, a question came in for you about the challenges. What are the biggest obstacles to the rollout of algal technology?
Yes, very important question, clearly. It'll take technology, investment, and economic viability, certainly, and government policy. So that's a very broad answer. We think one of the limiting factors has been this issue of poor mixing in existing large-scale photobioreactors. So we think that's something that our GEMS photobioreactor technology can address. And then at the other end, it's what can we do with the algal biomass? I didn't get to talk about that. I briefly mentioned hydrothermal carbonization, for example, high temperature, high pressure process that can convert biomass into biochars or hydrochars or solid fuels, or even at higher pressure into liquid fuels. But there are costs associated with all of that. So these are technologies that need to be worked out and scaled. Also appropriate algal strains. Some grow very fast, others have established high biomass or bioproduct values. So I hope that at least partially answers that question. It's a big question.
Yeah, so if we could just continue on for about 6 more hours, I think we'd have just as much to say. Kim, a question for you, although Dan, maybe it's for your purposes as well. What's the role that rural America can play in decarbonization? And what are some strategies for incentivizing farmers to do more of their, play more of a part in the transition to different energy strategies?
Yeah, well, I guess I'll start, although I do think that the work Dan's doing is quite relevant. Of course, being here at Carleton in the midst of this industrial agricultural landscape, I do spend a lot of time talking to farmers. I basically grew up in rural America. So one thing I would like to say about the politics of rural America is that we need to be a little bit careful about overgeneralizing. It's a huge territory. Rural Michigan is not the same as rural Nevada, obviously. But I do find that when I talk to farmers, I do think that farmers in general, there's particularly in kind of the big square states in the middle of the country, right? The big kind of deep red states, you'll find a pretty conservative political ideology characterizing a lot of farmers. What I find is that farmers may consult that ideology when they're deciding who to vote for. That doesn't mean they're going to consult that ideology when they're deciding what to do with their land. And I have yet to meet a farmer who is reluctant to consider renting his land out or her land out to solar farms or wind turbines. Basically, I think any farmer is going to look at a proposal like that, crunch the numbers, and do what's in their economic interest. So we're already seeing lots of farmers in the immediate area around Carleton looking into expanding and renting their land for solar farms. So I think that's obviously one of the big ways in which farmers can be kind of connected economically to this new energy economy that's taking shape. And I think it's really important that we do that. Because farmers may be a pretty small percentage of the American public, but they have a huge footprint. They just control a huge amount of private land.
Yep. Dan, I don't know if you wanted to pipe in.
Yeah, and this relates to a handful of other questions I've seen trickling through the chat. So in my discussion over the last year and a half, probably, or 2 years, I've been a little bit more integrated with some of the local farm community. And my perception is they're all very interested in ways to conserve their soil. And they, in discussing this field trial with Mike Peterson, our cooperating farmer on the project, we've considered, well, so how do we set this up so that it will be applicable and local farmers who see the results of our study might be interested in applying these soil amendments to their fields. And there's been a big emphasis on the soil properties and conserving the soil. And if you see a benefit to the soil you can convince people that the cost is worth the benefit that they get in addition to carbon sequestration. That seems to be a really key part of their thinking. And I think they're in difficult year-to-year positions of how they manage their lands. And they have to, if those decisions make sense to them from a cost-benefit analysis, it seems like they're willing to try a lot of different options. In terms of, this relates in some ways to I've seen a number of questions about costs of how to apply this enhanced weathering. We've been looking at there, as Kim said, these rural America controls a lot of land, and there's a lot of agricultural land in the state of Minnesota and in the US. And if the real benefits to something like enhanced weathering come from the carbon offset with more minimal benefits to agriculture, but no drawbacks, that's where something like a carbon offset marketplace, where you could keep track of the carbon accounting and have other financing come through so that the cost burden doesn't lie solely on agricultural communities. And I think in that model, there'd be a lot more potential buy-in from the agricultural community.
So question that's partly, again, for Kim, but also I think for Toivo as well, on the role of the utility systems that are currently in place. What role do they have in the expansion and the building out of new infrastructure?
Well, yeah, I mean, they actually have a very large role to play. And that's been I think one of the more significant areas where state level renewable energy portfolios have been pretty successful in kind of pushing the utilities towards renewable energy. Energy markets are highly regulated, of course, and there's a very complex kind of regulatory system in place, but it's definitely an area where government action and government policy can push more renewable energy, just because there really isn't a free market in energy. It really is already highly regulated. Toivo, you may have more to say about that.
Yeah, my internet connection just started giving me problems, so I didn't hear all of what you had to say. But as far as utilities, solutions such as if we're going to capture any significant amount of carbon from utilities, that will require quite a bit of land around those utilities. Some utilities have land. For example, we're trying to make a connection with cement plants. Cement plants produce huge amounts of carbon dioxide. There's one in Clarksdale, Arizona, not far from Fountain Hills here. And apparently that has some 3,000 acres available. How to use that land, certainly that raises environmental, ecological questions as well. So all of those considerations need to come into the balance. Another part is simply convincing utilities or ethanol plants or others that capturing their carbon can be economically viable and beneficial to them. We had another project a couple of years ago when we were producing terpenes, potential jet fuel precursors in cyanobacteria. And we made some effort to contact local ethanol plants as a clean source of CO2 for that purpose. Some were open to the idea, others were absolutely uninterested. So it'll take policy and convincing and also available technology and demonstrations of economic viability to get this off the ground.
And one follow-up from that, a question had come in earlier about any news about hydrogen production from algae and whether that is something that is still in the works.
Yeah, I saw that question. I can, if I can have I can show you a slide that I put up if that's appropriate.
Yeah, sure.
Okay, so let me see if I can find that. Okay, yeah, so hydrogen is of course a very interesting potential fuel. It generates no carbon emissions at all. Some algae do produce hydrogen. So far, that's pretty far away from any sort of commercial or large scale application. There are a couple of very interesting recent articles in Nature Energy, for example, that I saw, where investigators have linked a hydrogenase enzyme. So that takes hydrogen ions and those are reduced with electrons to make H2 gas. Algae and bacteria use that as a way to dissipate excess energy, but these investigators have linked these hydrogenase enzymes to one of the photosynthetic reaction centers, photosystem 1, so that involved that will directly funnel light energy into hydrogen production. So very interesting developments there. Certainly not yet at any commercial scale, though.
Thanks. We'll bring the conversation back to Carleton, if you don't mind. Dan, one of the earlier questions that came in had to do with your mentioning of the project in the Arboretum. And you mentioned that the Arboretum itself sequesters a certain amount of carbon dioxide. Just to clarify, how does it do that? And how do we know how much the Carleton Arboretum helps in sequestering carbon dioxide?
You'd think after so long of teaching on Zoom, I would remember to unmute myself. That's a great question. So that 903 tons of CO2 per year comes from an estimate from the I think around 2010, when Carleton was implementing its climate action plans. This was before I was here. And they made some approximations based on the transition from agricultural land that the college owned that's been converted to prairie. So big portions of the Carleton Arboretum, as many of the alumni that are in this call probably know better than I do, used to be in agriculture. So much of the Arboretum was formerly agricultural land that's been converted into prairie and reforested. And they made estimates based on studies of similar systems in similar areas to come up with that number. It's certainly a rough estimate of what the sequestration is for the Arboretum. And I think it's something that probably could be revisited with some more careful study, but that's where that number arose in the climate action plan process.
Kim, you had mentioned your sense of optimism about policies in the future. Several people have wondered, given the current makeup of the Supreme Court, to what extent should we be optimistic in thinking about federal policy?
Yeah, I'm not worried about the courts. I'm not worried nearly as much as many people are. There's a number of reasons for that. So I'll just mention a few. One is that with all of the kind of publicity and kind of attention on Trump's ability to kind of get judges, conservative judges confirmed, I think people have overlooked the fact that there are 860 federal judgeships, and most presidents get to appoint between 300 and 400 federal judges. Trump is topping out at about 200. So he's actually appointed far fewer judges than previous presidents, and he hasn't actually changed the partisan makeup of the federal judiciary as a whole very much. There's been, I think, one, maybe two changes in the appellate circuits, but he hasn't substantially changed the kind of overall partisan balance of the judiciary. On the Supreme Court, yes, he's had 3 Supreme Court appointments. That's unusual. And yes, they are all conservative. They were vetted by the Federalist Society. You know, judicial conservatism is a very rich tradition, and it includes a lot of different ways of thinking about the law. And when I look at the judges, the justices that are currently on the Supreme Court, what I see is a lot of differences. I do not necessarily see an emerging voting bloc, particularly not on something like environmental law, because the Supreme Court really doesn't treat environmental law differently than other kinds of regulatory bodies of law. So what I see is, for example, Roberts and Gorsuch and Kavanaugh all seem to be very different in their thinking about the administrative state. Alito and Thomas are very different. So far, I've not seen anything that particularly concerns me about the overall kind of complexion of the judges that have been appointed, both to the judiciary in general and to the Supreme Court in particular. So, like, I'm just not worried about it. I think that what we have are serious, professional, yes, conservative, but also just very professional judges who are going to do their job. And there other things that we should be focusing on, like what the administrative agencies are doing, what Congress is doing, what state and local government is doing. I think the ordinary voter has a lot of levers they can pull. And so that's where our attention should be.
Thanks. Yeah, thanks very much. You know, we've just got a very few minutes left here, but I would love it if each of you could just share a final thought with our large crowd. Thanks again to everybody who's been able to tune in today. Just final words of wisdom. Toivo, do you want to lead off?
Yes, always difficult to summarize a few words of wisdom, but I'd like to thank the audience for interest in this topic. Certainly a very important one, and I think what we've seen just from this short discussion is that it'll take many different kinds of efforts to make a dent in reducing CO2 emissions, other greenhouse gases, and taking a bite out of climate change. But we need to do that, and we need to work together. Thank you.
And Dan?
Yeah, I'll echo the thank you to the community that's participating. It was at one point hard to keep up with all the messages coming through the chat. And there's still many questions I feel like I didn't have a chance to get to. If anyone would like to follow up on email, you can find our information online, I'm sure. But it's been great to participate in this. There's, at least with the project I presented for the enhanced weathering, this is a new area for me. I'm really excited to be getting involved with it, and it feels great that we'll be able to do it on campus and have students involved. And as Toivo said, there's going to need to be a big mix of technologies and policies, like Kim was talking about, that try to address this huge problem. So it's nice to see so many people interested in trying to find the right mix.
For sure. Yeah, thank you. And Kim?
Yeah, well, I also agree that it's really heartening to see the level of interest in this topic, and also in the questions. Clearly, you guys are excited, you're interested. There's just a ton of energy behind dealing with this issue. So I just want to encourage everyone to be optimistic, be hopeful, go out, get involved, pursue smart climate policy in whatever arena you have access to, and take heart because it will work.
Thanks. That's a very, very Carleton advice there. Yes. Put your education to good use. Thank you. Well, thanks again, Kim and Dan and Toivo, for all that you've given us today. And thanks to everybody who tuned in for the show, whether this was your first Carleton Connects webinar or your 12th. I hope you'll tune in again next month. On January 14th, we'll be taking a live winter tour of the Carleton Arboretum, and we'll be joined by Nancy Breaker, the director of the Arboretum and a member of the class of 1981. So watch your alumni email newsletter for more details. And if you have any questions or comments, please get in touch with me, Christopher Brunel, in the Office of Alumni Relations. So thanks again, Kim and Toivo and Dan. And thanks to everyone. And we'll see you next month.
All right. Thank you. Thanks very much.
Bye.